But next up is another of our partners from across the pond over in Ireland. So the ICHEC site is, we have both Michael Browne and Niall Wilson here with us. Michael is going to do the presentation. And much like Tommy, ICHEC was one of our first partners to receive an IME test bed to be able to physically put this technology in place. ICHEC is the Irish Center for High Performance Computing. We've been leveraging DDN technology for about 2 years now. But in the past 6 months in particular, we're willing to take on the project, work with us to accelerate our application IO knowledge, work with us on bringing IME to market, and to take a test bed. So they put the test bed into production about 2 months ago, and we're going to be sharing results from that. Thank you very much.
Thank you. So, good afternoon, everyone. So, this afternoon I have the luxury of presenting other people's work and the luxury of having Niall here, our infrastructure manager, to take any tough questions. So, to be easy going. The other people in question are Gilles Savario and Marco Grossi, so all credit to them. So a little bit on ICHEC's background. We've been around for about 10 years with 27 or so staff, and we're, like many of the centres talking here today, we're a university centre, but a little bit different in that our mandate is a national one, and spreads across a few different areas. So we do a lot of industrial engagement, and the work we're presenting here today, I think, falls in under that. But we also work with the various public sector agencies, like the Central Statistics Office and Economic Location Service, which kind of surprised me when I've seen it recently. And then we work with the academic community across all of the universities and various other research institutes in Ireland. So from an infrastructure perspective, we're certainly not Texas big either, but we're DDN customers, happy customers, and there's a certain diversity there of SGI, which is relatively modest scale, but for various different reasons. I won't dwell on that. So I'd like to introduce as well Tullow Oil. So they're a company we work with, and Sean and Igor and Carl and Tullow are here in the audience today, I understand. So it's an Irish oil company, and not a whole lot of oil in Ireland, but to get around that, they operate in 24 countries, and you can see their revenues from last year over 2.6 billion, which their annual report tells me makes them Africa's leading independent oil company, where they do a lot of their work. So we've been working with them for quite a while on a code called Tortilla. So it's the Tullow Oil Reverse Time Imaging application. So it's a reverse time migration code. It has some unique features which I will talk about. Talk to the Tullow guys, see what they'll tell you. It's an in-house code for Tullow, and it's code developed with ICHEC. So I suppose the point to make here is, this is it's a real code for real work. They use this in production. On the technical side, a little bit about the code. It's a standard C++, OpenMP and NPI code. It's not that old, so there's not a lot of cruft or the like in that. It's quite modern and well optimized. There's 3 I/O modes, if you like, so POSIX, NPI mode, and in-memory or no I/O. So keep that in mind as kind of a best case scenario. So it's quite an efficient code. Achieves typically 30 to 50% of peak at scale, and scales a lot larger than what we'll be presenting in the test case here today. So the typical workflow for this code, and we'll ignore the compute side of it, the algorithms entirely, just think about it from an I/O perspective, is you do about half a petabyte of writes and half petabytes of reads, and at the end of the day, that gives you an output image, if you like, which is about 100 megabytes in size, and that's what your geophysicist on the ground wants to see. That takes 100 to 300 seconds, depending on various options, settings, and so forth. But then you need to do that several thousand times in a typical production run. So that translates to petabytes of I/O for a single production test case, if you like. So we've worked with DDN before in the oil and gas area in fairly separate engagement. So the opportunity arose to do some work with IME, and it's sounded very interesting to us, of course, from a technical perspective. So this is the cluster that was available to work on the problem, and we'll go into the specs. This kind of thing covered fairly heavily already, but maybe just to point out two things. So the compute node is relatively fat node, it's 128 gigs of RAM. It wouldn't be typical in a HPC compute node yet, at least. And if you look at the IME servers and compare notes with the TAC guys later, but just notice there that we had half the number of servers and we're seeing half the level of read and write. So certainly, so that's 2 points on the linearity graph at least. Well, maybe that's all you need. So the code porting side of things. I think the nice thing about this slide, from my perspective, is not a lot on it. I had to get a picture of the guys working on the code, just to add a little bit of color. Very little to say. Again, it's a standard code. We use the Intel compiler. It's a pre-GA releases, as we know from DDN. So you expect some changes. In this case, we had to do a little bit of pre-fixing on file paths, and for various reasons switch from Intel MPI to normally be used to MPA pitch. No big deal, you see that a lot in HPC applications. Currently requires a patched version of MPA pitch 2 and the addition of some libraries at link time. Again, pretty straightforward, and certainly less than you'd expect from unreleased products. So the experiments. So we take that cluster. We've done in the limited time available. We obviously wanted to get the results ready for to be here today. We have a small test case, medium, and a large. So there you can see kind of rough order of magnitude gaps between those, going from 80 gigabytes to 8 terabytes. And we looked at three I/O models, if you like. The in-memory, so that is a best case because you're just not doing the I/O, but that limits your problem size, of course. Straight traditional cluster file system, and then IME. So, to cut to the chase, the results, the IME results are here in red, and the in-memory blue, and then the normalized for the Lustre case. So in the small case there you see a significant speed up, and note that the IME one is getting pretty close to in-memory. On the medium test case, where you're getting a bit more realistic in terms of the problem scale, again you see the gap versus Lustre widen. Then in the large case, well, there you can't do the in-memory option anymore, so you can't compare, except to compare the difference between the two. And I really want to stress that we didn't want to be too complimentary here. So these times are for the total runtime. This is not just the I/O kernels, this is the compute included. There's a little bit of initialization excluded because when you do it thousands of times, that doesn't really matter. But that's total compute plus I/O. So there we see a 3x reduction in runtime, which is what the geophysicists want at the end of the day. The other graph, again, not a whole lot to say about that one, except for the fact that you see the IME performance there, the middle trace on that graph. It's perfectly horizontal. We just didn't have enough nodes to push that further. But even at that smaller scale, you do see the Lustre curve start to disimprove. So limited evidence there, but certainly evidence that the concurrent workloads are going to benefit as well at larger scale. So that's it for me, except to maybe revise that oft-quoted line in HPC that that IME can take what were I/O problems and push them back over the fence to the compute side of things again. Much to the Thanks to Ed and James and Rich and Amanda and DDN for their help, and most especially thanks to Follow for giving us kind of permission to take their code and play with it in this interesting scenario.